Greetings YouTubers, and welcome to episode 6 of my series, Lies That Flerfs Tell. Today we're going to be continuing our analysis of the flerf lie, there is no evidence that Earth rotates. In the last episode, I presented observational evidence from winds and ocean gyres that are exclusively consistent with a rotating Earth. In this presentation, I will move on to more direct observations of Earth's rotation, in particular using gyroscopes. Before moving on to that, however, I'd first like to discuss angles and the units that are used to measure them in mathematics. In school, we all learnt that angles are measured in units of degrees, with 360 degrees corresponding to a complete rotation, the angle subtended by a circle. However, when one moves on to higher mathematics, one generally measures angles in radians, with 2 pi radians corresponding to 1 revolution. The utility of this style of measuring angles follows from the definition of pi, in which 2 pi is the ratio between the perimeter or circumference of a circle and the radius of the circle. It follows from this definition that given a circle of radius r and an arc on that circle subtending angle theta in radians, then the length of the arc along the circle is r theta. Since the arc length L and the radius r are both length measurements and have the same units, it follows that radians are dimensionless. They have base unit of 1. Now that that's out of the way, we can turn our attention to direct measurements of Earth's rotation. One useful dataset might be images of Earth taken from distant satellites, such as these images taken by NASA's Discover satellite on May 29, 2016. But of course, flat earthers will completely dismiss this data with completely unsubstantiated claims of CGI. So let's move on. The first fully rigorous effort to try and isolate and measure the effects of Earth rotation were undertaken by Ferdinand Reich in 1831. At the Three Brothers mineshaft near Freiburg in Germany, Reich dropped a variety of weights down a 158.5 metre tall mineshaft. After 106 drops, he observed a mean eastward deflection of 2.84 centimetres. This agrees almost exactly with the theoretically predicted value for objects dropped from that height at that latitude. I've included the theory here in case any flat earthers want to stop choking on their own spittle and do something useful for a change like learn. The next major contribution to observing Earth's rotation was made by Léon Foucault, who, in 1851, publicly demonstrated precession of a pendulum, the rate of precession being almost exactly that predicted by theory. The following year, he published a paper describing his measurement of Earth's rate of rotation using a mechanical gyroscope. In fact, Foucault is the person who coined the term gyroscope. As with most mechanical gyroscopes, the central element of Foucault's instrument was a massive rotating disc. The disc itself was supported by a horizontal axle that connected it to the inner gimbal. The inner gimbal was supported by pins connecting it to the outer gimbal and was free to rotate around the lengthwise axis of the rotating disc. The outer gimbal was supported from above by a thread and from below by a metal pin and was free to rotate around the vertical axis of the rotating disc. The disc itself was accelerated to a velocity of 200 revolutions per second using a series of interconnected gears. Here I show a schematic of such an instrument on the surface of a rotating sphere, with its meridian of longitude shown as a white line. We are looking at the instrument from along the plane of rotation of the central disc. As the sphere rotates under the instrument, the central rotating disc will appear to tilt relative to the local vertical axis. This occurs because conservation of angular momentum dictates that the axis of rotation of the central disk must remain parallel to its original configuration. We now look at the same experimental setup from above. Initially, the angle between the meridian of longitude and the axle on which the central disk rests is 45 degrees. As the underlying sphere rotates, the elements of the gyroscope will reconfigure themselves to preserve the axis of rotation of the central disk. In this example, we consider a sphere rotation of 90 degrees. Moving our viewpoint to look down on the instrument from above its new position, we see that the angle between the local meridian and the axle on which the central disk is suspended is now 0 degrees. Which is to say, for an observer in the laboratory, as the Earth rotates, the instrument appears to twist around its vertical axis. To record this twisting motion, Foucault's instrument had a large needle affixed to the outer gimbal that extended over an angular scale. To measure the tilt of the inner gimbal, he used a microscope. By 1857, mechanical gyroscopes were returning measurements of Earth's rate of rotation accurate to within 0.2%. Mechanical gyroscopes would remain the most accurate and widely used instruments for measuring Earth's rotation for over 100 years. In 1913, Arthur Compton, future Nobel laureate, demonstrated a new technique for measuring Earth's rotation. His instrument, called the Compton Generator, used a glass tube full of water. The tube was allowed to settle so that the water in it became stationary. Once this had been achieved, the tube was rotated 180 degrees and the velocity of the water within the tube measured. Small droplets of oil or small flakes of coal dust were suspended in the water so that its velocity could be optically measured. Using this instrument, Compton was able to obtain a measurement of Earth's rate of rotation within 5% of the theoretical value. At the end of the 20th century, new techniques for measuring Earth's rotational velocity came online. For instance, in this 1997 paper, a new technique is described using a toroidal container full of liquid helium. The direction and rate of fluid flow through the aperture within the container allows the container's angular velocity to be determined. The accuracy of this technique scales with the radius of the toroid. For an instrument of radius 1 centimetre, a measurement with an accuracy of 0.5% was obtained after 1 hour. In this experiment from the early 2000s, a diamagnetic plastic ball was suspended in an immensely strong magnetic field. The precession of the ball relative to the laboratory was then recorded over time. The results of this experiment were in accord with the theoretical expectations for Earth's rotation to within 0.5%. In this experiment, a commercially available inertial sensor was used to estimate Earth's rotation. Great care was taken to ensure that the sensor remained level relative to local gravity during the experiment, and that the temperature within the laboratory was carefully controlled. After 16 hours of observations, they obtained a measurement within 10% of the theoretical value. That may not sound great, but given that they were using an off-the-shelf commercial piece of hardware, that's actually pretty good. As fascinating as these various techniques are, the current gold standard for detecting rotation is ring laser gyroscopy, first developed by Maciek and Davis in 1963. In its most basic form, this technique involves firing a laser source at a half-silvered mirror. Half of the laser beam goes through the mirror and is reflected around a circuit of equidistant mirrors back to the mirror, where it goes through once again to the detector. Simultaneously, half the signal is reflected back from the mirror and goes around the circuit of mirrors in the other direction, reflects off the mirror again, and is received at the detector. If the apparatus is stationary, then both beams will have undergone an odd number of reflections and will have travelled exactly the same distance, so they will be in phase when they meet the detector. If, however, the apparatus is rotating, then the mirrors will be rotating towards one of the beams, which will have to travel a shorter distance, and away from the other beam, which will have to travel a longer distance. As a result, the beams will not be in phase when they meet the detector. Consequently, when the beams are recombined, they will produce an interference pattern that can be analysed to reconstruct the rotation that the apparatus was subjected to while the beams were in transit. Predictably, for a technology that has been around for more than half a century, it has undergone quite some development since its original invention. This paper describes the operation of a chip-mounted ring laser gyroscope. While admittedly significantly less precise than cutting-edge instruments, this apparatus is still easily able to detect Earth's rotation. At the other end of the length scale, we find the ROMI facility at Fürstenfeldbruck in Germany. This facility consists of 4 ring laser gyroscopes arranged in a tetrahedral configuration with side lengths of 12 meters. It is sensitive enough to detect a variety of geophysical signals on local and global length scales. While these contributions are detectable, the dominant signal, as we can see from the figure, is that central peak, which is due to Earth rotation and is about 1 million times larger than the contributions from other processes. Between these two extremes, this tabletop ring laser gyroscope is 4 meters on a side and is capable of detecting changes in Earth rotation with an accuracy of picoradians per second. These observations, of course, are all based on laser propagation. Flat earthers predictably respond to this by invoking some sort of etherical effect. They do this despite the complete lack of any evidence supporting such a hypothesis. We can further disprove this hypothesis by noting that the exact same rotational effect is observed in counterpropagating clouds of Bose-Einstein condensate. When the clouds are recombined and their wave functions compared, they show the same interference patterns as were observed in ring laser experiments. Since, by definition, ether cannot influence the motion of material objects, this cannot be explained by etheric interference. So we find that for all styles of gyroscope, mechanical, pendulum, fluid motion, superfluid, magnetically levitating, ring laser, or matter wave interference, we always detect a 15 degree per hour drift eastwards, no matter the physical principle on which the gyroscopes operate. Flat earthers are forced to explain this by invoking a miraculous coincidence. All of these different experiments, based on different physical principles, are subject to different styles of error that all turn out to make it look like the Earth is rotating. It's willful obtuseness of the highest order. But we're nowhere near done burying them under our mountain of evidence. Shortly after the development of the mechanical gyroscope, it was realized that you could use the same principle to construct a gyroscopic compass. By fixing the gyroscope so that its only degree of freedom is rotation about its vertical axis, and then attaching the wheel of the gyroscope to an electric motor that rotates at a high speed, the instrument will respond by rotating into its minimum energy configuration. That is, the plane of the gyroscope will rotate so that the wheel is oriented along Earth's axis of rotation. This results in the needle of the gyrocompass always lying along the meridian from true north to true south. These instruments were quickly recognized to offer several advantages over magnetic compasses. They point to true north, not magnetic north, so they're not subject to magnetic declination. Nor is their accuracy at all impacted by the large amount of ferromagnetic metals that are commonly used in modern shipbuilding. As a result of these advantages, these instruments have played a prominent role in commercial ship navigation since the early 20th century. More recently, fiber optic versions of these instruments have become available. As is so often the case, flat earthers have absolutely no physical mechanism to explain why these instruments work as they do. We can also track changes in Earth's axis of rotation by precisely comparing ground station positions relative to our constellation of navigation satellites, or by precisely analysing arrival times of signals from distant celestial objects at ground stations across the Earth. These two techniques produce consistent results and allow us to track polar motion with great precision. We can use the same techniques to track changes in the length of day. That is, the time it takes Earth to complete one rotation relative to celestial objects. A change in the period of rotation obviously corresponds to a change in the rate of rotation, and these changes in rate of rotation accord precisely with those detected by ring laser gyroscopes. Again emphasizing that no matter which data set we use, we always get results in agreement with an Earth rotating at approximately 15 degrees an hour. Okay, that might be where I wrap things up for today. The bottom line is that I presented a dozen different techniques for determining the rotation of Earth, all of which produce consistent results, despite being based on widely divergent physical principles. The simple, inescapable conclusion is that the available evidence is entirely consistent with the fact that Earth rotates, and utterly inconsistent with the claim that it is stationary. No amount of infantile foot stamping, name-calling, or gibbering wits at word salad is going to change the data. Thank you very much for watching. I really do appreciate it, and I hope you'll join me next time when I will be discussing precession and the motion of celestial objects.